Hey, P-Stats kids. We are going to start Chapter 7 now. We are going to be looking at sampling distributions. Let's go. Alright, we got to start at some point, 7.1. We're going to look at the difference between a parameter and a statistic. We're going to make sampling distributions. We're going to use them to evaluate claims, 5% rule. We're going to distinguish between distribution, population sampled, and sampling distribution. Determine if it's unbiased, and we're going to look at sample size and how it relates to variability. Statistic, what's it called when you ruin a surprise? Spoiler, the bigger the sample size, the less variability. Okay? A lot of this we've talked about. So first thing I want to talk about is what is the difference between a statistic and a parameter. A statistic is a number that we got from a sample. Alright? A statistic is an estimate of the parameter, and a parameter is the number that describes a population. Like mean, if you have the mean of a population, that's the parameter of the population. Can you usually know that for sure? Not always. But make sure you know that when you take a sample, that's an estimate of the population mean. So the sample is a statistic. Like the mean of the sample is a statistic. The parameter is the real life. Okay? So like, know these symbols. Wow, that's a small highlighter. Gee golly, I need some. Know these. This chart is very important to know. We will talk about it in class on numerous occasions. It's blue da-boo-dee da-boo-dee. Okay? Okay? Let's look at an example. So we're going to look at this and we're going to identify the population, the parameter, the sample, and the statistic in each setting. So A, the Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Our response, 160 said yes. So let's look at A. So they polled 515 randomly selected U.S. adults. So the population they're looking at is United States adults, right? The parameter, we want to know what's the proportion of everyone in the United States who's an adult that believe in ghosts. The sample is the 515 people you selected. And the proportion, the statistic, the P with a hat, it's actually called P hat, is the 160 out of 115, or the 31% that said they believe in ghosts. That statistic we got to estimate the parameter. Okay? Phew. Alright, let's look at B. You guys can read. Take your time. For B, they want to know when it'll be well below freezing. So they set the thermostat at 50 and wants to know how low the temperature gets in the cabin with the thermostat set. So she takes the temperature 20 random times, and the minimum reading is 38. So population is all the time throughout the day. Okay. The parameter she wants to know is what's the true minimum temperature in the cabin. Like what's the lowest it gets. The sample is the 20 readings she took at randomly selected times. And the statistic was the minimum that she got, which was 38. That estimates the parameter. Read this. Know it. Alright? Because many students lose points on the practice or on the test. Because when they're talking about parameters, they use sample statistics. Okay? So make sure when you're talking about the true population, you're using the word true or for all. Okay? Why you no click? Alright, so remember S and P. S. Statistics come from samples. P. Parameters come from populations. Look at, there's even boxes and they're color coded. Now we've talked about this before. If you're taking, there's sampling variability, right? If I took a sample of whose favorite color of M&M, it's going to be different every time because you're not going to get the same people. Okay. Sampling variability is the fact that different random samples of the same size can get different values, right, for a statistic. So look at this beast. Let's say we did a penny. I don't know if we'll actually do this. So this is, you took samples of 5 pennies, and you took the average, the mean of those pennies for the years that they were printed. Okay? You can see they aren't all the same. You have some from 91. You have some from 2012. You have some from the different means, okay? Because not all 5 pennies are the same. But over time, you can get a pretty good estimate of what the actual average year is. So let's take a look at this piece. Oh, I need my Mobi actually for this one. So John and Carol have 4 grown sons. Their heights are 71, 75, 72, and 68. What are the 6 possible samples that can be taken for their height? That's a good question. Oh, well, there they are. Cool. Well, I just clicked it. I'll put my face over this. So you could have 71 and 75, 71, 72, 71, 68, 75, 72, 75, 68, 72, 68, right? It's all the possible combinations of the 2 sons that can be selected, right? And when I dot plot them, I get that. Right? That's a sampling distribution, just like a probability distribution, has every possible outcome. Now, whoa, I went too far. Now, I took the means and I plugged them out there, right? So this was A, this is B. You add them, divide by 2, plot the means. All right? You good? Now range, I subtracted them, I plotted them. Again, sampling variability. We will be doing this in class, trust me. Got a different problem. Pause it, read it. Pretty much there's a bag of 200 poker chips. 100 are red, 100 are blue. And they're going to randomly grab 20 chips from the bag. And they're going to say, they're going to look for evidence that less than half the chips in the bag are red. So, Jenna grabs in. Jenna, stop it. Grabs out her 20 chips. 7 are red. Is that convincing evidence that there's less than half of the chips are red? So, Jenna's sample, her p-hat, 7 out of 20, which is 0.35. And that's less than 50. So in my head, I'm like, well, then obviously it's less than 50%. But we have to use statistics to prove it. So let's give explanation of what happened. So it's possible that the teacher's telling the truth, but just by chance, she grabbed out less than 50% red, right? That's one way. It happened by chance. The other way is Mrs. Lynn's a dirty liar and not half those chips are red. Okay? So either she's lying or Jenna just by chance had 7 out of 20 red. So how do we show that? So what we do is we make a simulation, because we can't do this by hand and just keep taking samples. If I use computer simulation, it will do 500 simple random samples of size 20 out of the 200 chips. We will be doing this in class. And this is our p-hat. Every dot represents the portion of red that they got in that random draw. Okay? At 0.8, there is 1. 1 time out of 500, 80% of the chips were red. So that meant 16 out of 20 were red. So, yeah, there it is. 1 time in the simulation out of 500. So really rare. So if you grabbed out a handful and 16 were red, you would say, Miss Lynn, you're a liar. There's a very low probability of that happening. Okay? Now when we look at the Jenna's poll, the 7, that'd be 0.35. When I look at 0.35, there's a large number of 0.35 and lower that happen by chance. So, could be legit. Alright? So no, Mrs. Lynn's probably not a liar. There's many simulated samples where p hat was less than or equal to 0.35. Could have happened by chance. 5% rule. If it's less than 5%, probably a liar. So is there convincing evidence? No. Because it's not surprising that you have a 0.35 proportion alone when p is 50. So there is not convincing evidence that she's a dirty, no good liar. Mrs. Lynn was actually my kindergarten, not my kindergarten teacher. She's a kindergarten teacher here. Never had her. Went to a different school. So, I want to compare something. So, the idea of taking many samples from the same population and collecting it will lead us to a good estimate of the parameter, okay? So think about this. The population distribution gives the values of the variables for all the individuals. So that's when we do all. The distribution of sample Dist gives us the variable of the individuals in sample. And the sampling distribution displays the values of all the possible outcomes of the same size. Sorry, I did that really quick. Let's do it again. That was cool. The population distribution, the 50-50, gives us all the individuals. One piece of sample data gives you variable for those individuals in the sample, just those in sample. And if we make a distribution of all the sample proportions, it will show all the values of p hat from all the samples of the same size. Sorry guys, got a phone call in the middle of this. Alright. Terminology matters. Never just say the distribution. Never say this. Be specific. Use context of the question. The distribution of number of hot dogs eaten in a day. The distribution of number of free throws Mr. Holder makes out of 10. 0. So make sure you don't use ambiguous terms. Read the question. Use the question. Okay? Don't lose points. So a statistic should be unbiased to use to come up with the parameter. Alright. It's unbiased if the statistic is equal to the value of the parameter. Like, look at this. Our sampling distribution shows 0.5. We know the population is 0.5. It's not biased on it. We got what we were supposed to get. It's unbiased if we get what we're supposed to get. How do you know the true population? Don't ask me that. It's tough. So let's look at the height sampling question. Whoa! I'm a ghost. All right. Same John and Carol's 4 sons, 71, 75, 72, and 68 inches. Poor guy. So would this be unbiased? So the mean of the sampling distribution was 3.67. Okay, we add all those up. But this was the difference. The range of the population is 75-68. So because the sampling distribution of the range is not equal to the actual range, this is not unbiased. It means it's biased. It's no good. Now, how do we get an unbiased estimator? There's no way to do it because you don't know the actual parameter value. Yay! But if you use large, random samples, you will get close to it. Okay? Look at a sample of 100 is more spread out. Sample of 1,000. with that sample 1,000, we have a pretty good idea of what the true parameter is, what the true population is, using our samples. All right. Sometimes they're obvious, sometimes not so much. Okay, we'll talk about this more in class. I'm actually going to talk about this in class too. I think this is more fun to do in class. So that's where I want to end it. Read it, love it. See y'all sometime. Have a great day.